we are going to give you a condensed version of Stephanie Fitchett's paper on Bezout's theorem, just to give you a taste for algebraic geometry and some of the things that might follow from it. So the theorem itself makes a statement about the multiplicity of the number of intersections of any two general curves. To understand that, we're going to look at a slightly simpler example of not just any two curves, which can be any dimensional. We're going to look at curves in the affine plane. In high school algebra, we define curves as explicitly as like y equals x squared. Yet in algebraic geometry, we're going to define this same curve as the zero set of the curve f of xy equals y minus x squared. The necessity for this is going to come up later when we have to manipulate curves, and this definition simply won't be good enough. Now, looking at the number of intersections, some things might pop out. Since we're not necessarily caring too much about one specific curve, we want to look at the maximum number of intersections of families of curves. In this example, we have an ellipse and a degree 4 curve. Maximum number of intersections would be 8. Similarly here, maximum number of intersections would be 4. And the maximum number of intersections here would be 9, all 9 of which are actually displayed in this example. From that, we're able to gather that the number of intersection points has to be less than or equal to the product of the degrees of each of our defined curves. But this inequality doesn't really give us much information, specifically when we're talking about the general cases of curves. In this example, where we have a degree 2 polynomial and a line, we can see that it can either have 2, 1, or none intersection points. So how do we make all of these equal to perhaps strengthen this statement a little bit? Well, one way we can do that is by looking at the complex plane, accepting complex inputs, and also looking at the multiplicity. This curve has 2 intersection points with the line of multiplicity 1. So if we sum those, we get 2. This curve has 1 intersection point of multiplicity 2, again a sum of 2. And while this point doesn't have any intersection points with the line, if we accept real inputs, accepting complex inputs, we get 2 intersection points of I and negative I, each of multiplicity 1, which again gives us a sum of 2. So what if our curves were lines? If we have lines, there's no way to make them intersect using the complex plane or any multiplicity trick. So for that, we're going to need the projective plane.
As Julian mentioned, we're going to consider the case of parallel lines. Ideally, if our conjecture formula is true, every single pair of lines will have exactly 1 intersection point, no more and no less. One place where this is tricky, parallel lines. They don't intersect in our normal plane. No matter how far we go in either direction, they won't run into each other. So the question arises, how do we force them to intersect? What we're going to do is we're going to add what are called points at infinity, which is where we say, okay, let's just say that these 2 parallel lines intersect at some point way over there. We're going to chuck that point into our plane. We have to do this for every possible slope of a line through the origin, because if lines have different slopes, they already intersect somewhere in our normal plane. So if we had their point at infinity for that given slope be the same, they would intersect at 2 points, which we also don't want. So we're going to add 1 point at infinity defined by the slope of that line. If we have a point that lies in our normal plane, we're going to add a third coordinate and have it be 1. So for example, here we have the point 1, 1, 1. In the projective plane, here's the point 1, 2, 1. Our points at infinity, we're going to define where the point x, y, 0 is the point at infinity for a line with the slope y over x. 1, 1, 0 is going to be the point at infinity for lines of the slope 1, 1, 2, 0 for lines of slope 2, etc. So once we've defined the projective plane, the question is, how do we take our algebraic equations for curves, bring it into that space, and then bring it back to find some information about the intersection points of these curves in our normal plane? And that is the process of homogenization. The idea is to make all terms have the same degree. This is one place where it's important to think about our curves as the 0 sets rather than typical functions that we're used to, because we want to consider y as something that needs to have a specific degree as well. So you multiply any term that has a different degree by 1 copy of this capital Z, and we switch into our projective plane with these capital letters. So for example, with x equals 1 and then y equals x squared, to find their intersection points intuitively with our conjecture formula, we want them to have 2 intersection points. We already know what one of them is, and we want to find what that other intersection point should be. This first equation, when we homogenize it, we get x equals z. Second equation, x squared minus yz equals 0. Solving these as a system, we get that x can be equal to either 0 or y. This is capital X here. So that x and z will both be 0, and that means that y could be anything here. This is x squared minus yx equals 0. If x is 0, it doesn't matter what y is. So this gives us the 0, 1, 0, which is the point at infinity for any vertical line. And then the other case where x equals y, we have x equals y equals z. We can dehomogenize, jump back into our normal space, and we have that x equals 1 from one of our original curve equations, and the point 1, 1, 1 is the other intersection point.
So far, Julian and Leo were discussing of how we can extend these curves with homogenization and projection planes to find general solutions. The important thing that we should establish is how can we generalize this further and formalize these ideas, which can be done with what we call Basel's theorem. So Basel's theorem states that if C and D are complex projective curves with no common components, which we will cover, then the summation of the intersection multiplicity of C and D at point P would equal the degree of C multiplied the degree of D. This theorem is basically what we were doing with affine planes, where we just said the degree of C and D is an upper bound for the number of zeros for curves. So an important thing to establish is what is a common component. So an example of this would be for two curves C and D with degree 1, we have C is the function f of x and y equals x and y, and D is the function g of x and y equals x squared minus x times y. To get these two functions to equal 0, we can have that C is the union of x equals 0 and y equals 0, and D is the union of x equals 0 and y equals x. And as we can see, both C and D share x equals 0 as a infinite line as a solution. So basically what we're saying here is that having common components implies an infinite number of points of intersection. But while we can establish what the definition of common component is, this leaves with an important question of how do we define intersection of multiplicity through plane projections.
Picking up where the others left off, we have this as our intersection multiplicity. And all those previously defined, we're going to do it slightly differently here to capture more of the nature of our problems. So here we're going to set it equal to the dimension of this ring here, which we denote as O sub p, which is a ring of rational functions defined at our point P, mod to the functions f and g at that point, where functions little f and little g, taking into variables x and y, are corresponding to these here, where the capital X, Y, and Z come from the homogenized manipulations we were doing earlier. Now to make this a little bit more clear, we have an example from the paper here, where we have the function f of xy equal to y minus x cubed, which will be equal to 0, and then we also have g of xy equal to y, which is also equal to 0. O sub p, mod f and g at point P, is congruent to c of xy over our functions here. We just substituted them in at xy. And then that is congruent to this here, since we said y is going to be 0. Think of it somewhat as just plugging in y equals 0 here and simplifying it. We localize the ideal corresponding to x, and then that provides us with this basis here for our expression. In summary, you can find the multiplicity in 3 steps. First, you want to simplify the expression of your local ring of the function. After you do that, you'll notice your factor ideal of the quotient ring contains a product of linear factors. Step 3 is the power of the factor corresponding to the ideal where you localize your ring is equal to the intersection multiplicity. It basically allows us to kind of fix some issues that come with parallel lines and the inequality in Basel's theorem when we want a strict equality.